In this lecture, we're going to talk about fabricating the wax pattern, sprueing, investing, casting, and soldering. We're going to start with describing the dental waxes. So dental wax compounds were used in dentistry, which are a mixture of individual waxes of natural or synthetic origin. As with all other dental materials, each component in the mixture is selected to give a specific property best suited for the procedure being performed. Depending on the purpose of the wax, modifiers are included to change the melting range, increase or decrease the stickiness, or impart a distinguished color. Dental waxes are supplied in various shapes, sizes, colors, and composition. It's better for us to become familiar with their uses and manipulation and be prepared for the variations in the behavior of different waxes supplied by the manufacturers. What's important to remember is that for each type of procedure, especially when we do a waxing for a coping or a framework, we have different type of waxes so that we can use. We have the sculpturing wax or the carving wax, which are ash-free waxes. Also, we have a margin wax that it's very important to use because the margin wax has better memory. So every time we remove the casting from the die, the wax has the memory to come back to its original shape. And that allows us to have a margin that is accurate with the margin of the preparation. Also, it's very important to know the melting range of the waxes because if we melt the wax at a higher temperature, we may burn out some of the properties. One note, please keep in mind the difference between a melting range and a melting point. A melting point describes the melting temperature of one element. So for instance, if I have wax that's made of beeswax and I'll melt it, I know, let's say that the melting wax for the temperature for the beeswax to be melted, it's, let's say, 70 or 80 degrees Celsius, okay? Melting range describes the melting temperatures for a compound material. So like we have waxes that are made from different materials, natural and synthetic waxes. Each element of that compound wax has a melting temperature, but combined as a new material, the compound has a melting range. So for instance, we can say that for, let's say, margin wax, the melting range could be somewhere from 120 to 160 degrees Celsius. So that's a very important distinction when we're talking about melting temperatures, because that's we want to obey by those temperatures to keep the properties of the material that we're using. So blackout wax we may use also for fixed restoration, especially in the areas that we may need to black out some undercuts on the preparation. Also, the wax comes, if it comes in sheets or wire, they come in a different thickness, and the thickness it's measured in gauge. So the gauge indicates the thickness of the wax. Inlay wax, its composition is 60% paraffin, 25% carnauba, 10% resin, and 5% beeswax. It's hard, regular, and soft, and this is the type of flow. The carnauba wax reduces the flow, and the resins added to the wax increases the flow. Um, the inlay pattern wax might burn out completely, no residue left in the ring, and all waxes must be softened with the heat but not become flaky. Must be able to be trimmed to a fine margin with no chipping, and also must flow at a workable temperature. Organic pattern wax should be used for pressable ceramics to avoid contamination and to allow a clean burnout process. Like I said, there are many waxes today that they actually are ash-free waxes, that they don't leave any residue during the burnout stages. Margin wax has a higher detail, crisp and sharp, excellent for minute details, and it's used at the margin. Sticky wax is composed of beeswax and resin. It's very sticky when it's melted and becomes hard and brittle when it's cooled. Usually it has an amber color, and it's used to temporarily glue together models for articulation or crowns for soldering. Um, one property of the sticky wax is that it has a maximum shrinkage of 0.5%. Blackout wax, it's higher melting temperature than the inlay wax. It's soft and tacky when it's hot, and it's used to black out the undercuts on the dies. Like I said, the gauge is a measure of the thickness of the wax, and then the term is applied to the diameter of the metal wax, wires. Um, Also, it's used when talking about sheet of metal and sheet of thickness. Um, Usually, um, the bigger the number of the gauge, the smaller the thickness of the wax. So, um, a gauge number 12, it's actually smaller in size than a gauge number 6. Composition of dental waxes. So their composition of, they contain natural waxes, synthetic waxes, fats, gums, and oils and resins. Natural waxes are found in natures, and they have added pigments to give the color, the desired color. Um, Natural waxes are found in nature, and such as paraffin, which is derived from oil, and it melts at a temperature between 40 to 71 degrees Celsius. Plant from such as carnauba wax, insect from bees, beeswax, and animal sperm oil, dental floss. Type of dental waxes that are used for patterns, which their characteristics are tacky, inlay, casting, base plate wax that gives that we can use to a full contour wax up. Processing waxes that are used for boxing, utility, sticky waxes, any other auxiliary waxes, and impression waxes that are corrective bite waxes, which are usually done to take a bite registration, and we use that for mounting correctly the case. Characteristic of dental waxes are achieved by the addition of different ingredients, and like we said before, there are a combination of natural waxes, synthetic waxes, resins, and other pigments that increase the properties and give us the desired color for those products. Characteristic of waxes, their melting range. The paraffin melts between 44 to 62%. It's 62 degrees Celsius. Carnauba 50 to 90 degrees Celsius. Also, every dental material, including dental waxes, they have a thermal expansion. So thermoplastic materials soften when heated, and they're hardened when it cools. So when they expand with the heat, when they heat it up, they expand, and when they start cooling off, they contract. The expansion accounts for failure of the casting, and the flow also increases as the melting point is reached. High flow of the waxes, it's about mouth temperature. So that's why sometimes when the dentist uses specific wax to take a bite registration, he uses a wax that doesn't soften in the patient's mouth, so it stays hard and can take an accurate record of the patient bite. So how we prepare the dye? First of all, the dye is trimmed and ditched, and then the undercuts are black out. Then we're using a wax pencil to identify the margin. Then we apply a dye hardener to seal the surface of the preparation and also to increase the strength of the margin. Then a thin layer of dye spacer is applied, uh, let it dry, and then the second dye spacer layer is applied. With the dye spacer, we have to be careful not to overextend the dye spacer over the margin. It has to be at least 1 millimeter space between the dye spacer and the margin to account for the cement. And then the dye is completed. Let it dry, the dye spacer. Before starting the wax up procedure, dye lubrication is applied to the dye on all the surfaces, including the saddle area, the proximal surface, the occlusal surface of the opposing teeth, and also the adjacent teeth, especially on the contact areas. So when we're talking about waxing a porcelain fused to metal coping, first of all, we're going to black out the undercuts on the dies if there are any. Like we said before, we're going to apply the dye hardener. It's indicated that the dye hardener it's painted on the margin, so it seals the margin and make it stronger. But the dye spacer should be applied above the margin. When we start the waxing procedure, there are different methods to do it. We can use a dipping unit. So this is like electric container that gets warm. We can set up the temperature and it melts the wax. Then we can take the dye, the lubricated dye, insert it into the dipping unit and remove it slowly from there. And the wax, it forms like a little coating on the wax surface. And that should be about 0.5 millimeter thickness of wax. The advantage of using this method is that it gives us a nice uniform thickness of the coping, and then we can start building up the shape of the coping using carving wax. Also, in waxing, we can use prefabricated plastic copings that are formed by vacuum press unit. A plastic coping gives the tightest fit and a spacer might be needed. So that spacer, dye spacer might be a little bit thicker because when we apply a vacuum form plastic coping, it's going to be very tight on the coping. Wrap around, so we can use a wrap around the sheet around the dye and seal at the seam. In terms of this method of wraparound is not very accurate and the thickness might not be uniform. So that might be a faster way to do a coping, but it's not always the most accurate. What we need to do in any of these methods, it's very important to trim the excess exactly at the margin line. So we don't want to have the margin overextended. Then we can start building up the lingual collar, 3 millimeter in high and 1.5 millimeter wide on the lingual side of the coping, wrapping around to proximal sides. Build up very slight color reinforce on the facial margin to ensure casting. This will be removed after casting. So there are some designs that we can use for um, the coping in doing the wax up procedure that kind of gives us ensure that the casting it's complete and accurate, but also provides enough um, structure for the porcelain that will be applied afterwards. Um, No undercuts, sharp spots, undefined area, unclean finishing line, or areas of excess porcelain. Again, we have to be aware of how we design um, the coping or the framework. For instance, the book always tells us that the minimum thickness of the coping should be 0.5 millimeters, right? Well, it's not always the case. So for instance, if let's say I'm using base alloy for the um, coping, which is a stronger metal, right? I can thin out that metal maybe to be zero point 0.3 or 0.5, zero point 0.4 if I don't have enough clearance from the occlusal or proximal areas to put the porcelain. On the other hand, if let's say the preparation is too short and I have too much space and I know that my porcelain has to be about 1.5 to 2 millimeters in thickness and I have more than that with the coping, then I have to think about it how I can provide the support for the porcelain in the coping. So one way to address this issue is to increase the thickness of the coping in the area where we have too much space. Also, the lingual color. Sometimes if, let's say, depending on the preparation and depending on the margin, but let's assume that we have a case where the preparation has a bevel margin and that it's subgingival. And therefore we can have a margin that it's very thick because being under the gum is going to push the gum away and it's going to create more problem for the patient. So in cases like this, sometimes the metal color around the margin is left exposed, so there is no porcelain applied all the way to the margin. But that metal has to be made as a color to give support to the porcelain. Also, in cases like this where we have a bevel margin under the gum, it's good to have a metal that it's sealed with the margin of the tooth, and also it can be polished. Metal can be polished very nicely. The porcelain sometimes it's a little more porous, letting bacteria and food to get a little trap on the surface. But having metal that it's highly polished, that kind of blocks the bacteria or the food to get trapped in there. So this is the method of dipping the wax. So we insert the dye into the melted wax. The anterior dyes, they're inserted straight at 90-degree angle, and then take it out very, very slowly, and then rotate it a little bit so that bubble of wax on top, it doesn't stay there. So it just coats the whole dye in a uniform thickness. And for posterior dies, we insert the die at a 45-degree angle, and then again we take it out very, very slowly, and we rotate the die again to not have that little bubble on top. So when we're talking about design of the substructure, we have to think about it again, how much the doctor prepped the tooth, how much it's the requirement for the thickness of the metal coping, and also how much room we have for the porcelain. So we have to be aware that applying this knowledge, it kind of allows us to see and to visualize how the final restoration is going to look. So if we look at this picture, we can see that the metal actually it's cut a little short on the labial by the margin, because for aesthetic purposes, we want to have porcelain in there so it doesn't show that grayish line by the margin. Um, so positive waxing, it's adding small increments of wax and build up to proper shape and form of function. And negative wax, it's build up a bulk of shape and smash the opposing dentition to warn the wax and cut back. So these are different type of techniques to do a wax up. Positive waxing, which is mostly used by experienced technicians, because adding small amounts of porcelain where needed kind of allows you to develop a design in a faster and more accurate way. The negative waxing method, it's used when, let's say, we are in a rush and we just have to do something really fast. I don't recommend this method because, like it says here, we put a lot of wax on the die and then we close the articulator. We use the opposing to smash the wax to give us kind of like where the cusps or the teeth characteristics are, and then we go ahead and cut back. The problem with this, like every time we close the articulator on wax, it's not a strong material. We may have fractured the wax by closing too hard the articulator, or we can damage and distort the design. So um, if that method is used, it has to be very careful and gentle when closing the articulation. So in terms of the designs, there are different type of designs for the framework depending on the preparation. If it's an anterior or posterior preparation. For the anterior framework, we have to have a little more lingual support, but we have to think about in terms of aesthetics for the labial to have less showing of the metal and have enough clearance to add porcelain. The purpose of a lingual collar and proximal uprights when waxing a ceramic copings or a matrix when constructing porcelain jacket crowns is to give more support for the layering porcelain. The proximal uprights can be incorporated into the design of a coping when extra support for porcelain is needed or when joining two or more units together. So when we're doing the contact between units of a bridge, right? So that collar can be extended all the way up to the contact between the units. The posterior design for the framework, again, we have to be careful, especially on the posteriors where the forces are greater. We are mostly concerned about the function. So we are thinking about to develop a design that gives enough support for the porcelain and it's not breaking. especially when we're talking about cusps, right? Young people that have cusps that are a little bit longer and more detailed, we have to be careful to put enough um, metal substructure to support that porcelain. In terms of the maxillary posterior framework, again, we have here different type of designs. So the first, starting from the left, it's a more aesthetic crown where we have a little bit of more lingual color to support the porcelain. The second picture from the left, we have the color with the proximal metal contacts, which give enough support for the porcelain. The third picture and the fourth pictures from the left, those are mostly used in cases where the patient has a tight bite or bruxism, where the porcelain, where the metal is carried onto the occlusal surface. So it's the same idea here for the posteriors for mandibular. So we can see from left to right, left more aesthetic, very defined color. The second from the left, it's the color with the proximal in metal. And then the last two are the occlusal and the lingual in metal. And those are good cases for patients that have a really strong bite. Many times, especially patients that they have bruxism and maybe they don't wear a night guard during sleep, during the night they grind their teeth. And if they have a crown, the porcelain may fracture. So maintaining that metal on the lingual and occlusal give a longer longevity of the restoration. In terms of the margins, so we always talk about how the margins should be developed and in what cases each type of margin can be used. So a chamfer margin, it's a margin that it's more like a round margin, and this is a good margin because it allows the porcelain to bond better with the metal because there are no sharp edges. A bevel, again, this is a type of margin that it's mostly used for cases where the margin is subgingival and the margin is very thin. So usually on the bevel margin, there is no porcelain applied. The porcelain is applied from the collar up. Okay? So the margin is left in metal and polished very well. The shoulder or the butt joint. This is a kind of like a 90-degree type of margin, and it's very much used in cases where we have a short metal framework, and then we leave the margin exposed and we add porcelain to close that margin. So actually the margin of the restoration will be in porcelain, not in metal. And that's for cases where aesthetics plays a big role. Feather edge, which is kind of the same, similar with the bevel. Again, this is a margin that it's very thin, and the metal has to be very thin on the margin, and if there is any porcelain applied to there, has to be everything very thin just to cover that margin. So what we need when we start doing the wax up, we need a separator or a lubricant applied to the dye. We need a dipping unit to have the dye, the wax melted. We need, after we start doing the wax up, we need to check the centric contacts, the centric occlusal, cusp to fossa or cusp to marginal ridge. Check the centric movement relationship, the lateral movement, and the protrusive movement. Also, the anatomic and functional contour of the wax pattern. So we're looking at the incisal or occlusal contour, the labial and buccal and the lingual contours, mesial and distal, proximal contacts, marginal ridges, embrasures. Very important when we're talking about doing a full wax up. We always concentrate on the margin and also on the anatomy, which is good. But very important, it's also to concentrate on the contacts, mesial and distal, and the embrasures. The gingival embrasures, they always have to be a little bit open so the patient can clean. If the embrasures are closed, the gingival embrasures are closed, the patient cannot floss or use a proxy brush to clean. Therefore, the gum might be damaged. Okay, so those are things that we have to keep in mind in addition to the anatomy design and the margin. Okay, and again, when we ready to finish the wax up, always check the margin to make sure that the margin is sealed. There are no voids in there, and it's nice and smooth. Again, when we do the wax up, we always have to check the bike. So that's why we mount the case in an articulator to perform how the patient moves, up and down movement, and also from side to side, which mimic how the patient chew their food, or when we talk, we move the lower jaw from side to side. So those are the important movements that we have to apply to our wax up for having a good design. So if we're looking at the maxillary contour, embrasure, and occlusion, so always make sure that we follow the gum line and also the contours of the teeth. So if we have to copy a lateral, upper lateral, and number 7, we have to make sure that we look at number 10 and we copy the same shape. Also, like we said before, we have to be aware of the embrasures. So keep those embrasures open. If we keep them too open, then they create what's called a negative space. And every time the patient talks or, smiles, we're going to see that black triangle between the teeth, which are not aesthetically pleasing. The same for the lowers. So when you have a chance, please watch the following video. It's very interesting to see how the jaw is moving. And even though we're using what's called a semi-adjustable articulator, the one that we're using has the upper part of the articulator moving, which is the opposite of the natural way. If you think about it, when we talk, when we eat, right, we move the mandibular. We don't move the maxillary. Okay, so this video kind of shows what happens when the lower jaw is moving, and how the relationship between the upper jaw and the lower jaw plus the teeth, and they relate to each other in different movements. So very important when we do a wax up, we keep talking about that we have to maintain a certain thickness depending on how much the preparation it's cut down. So and also based on the manufacturer recommendation. So it's always recommended to use a wax caliper to measure the copings, or in general any wax um, design that we do uh, has to be measured. Careful when we measure the margin. When we put a caliper by the margin, if we press too hard on the caliper, that might chip the margin or damage the margin. So very, very gentle with that. Um, so the porcelain bearing area of wax pattern should measure from 0.3 to 0.5, depending on the type of alloy used and the requirements of the case. We have to leave sufficient wax to ensure that the pattern can be cast completely and metal finished to the desired final thickness. And sometimes, for instance, we keep talking about restorations that are going, they have a bevel margin where the metal is left without porcelain, but the metal becomes very thin when we finish that, because it has to be sealed with the margin of the preparation. But during the waxing procedure, if we have a very thin area of the wax by the bevel, we can make that wax a little bit thicker during, for the casting procedure, because if the wax is very thin, we might have a miscast. So we can make that margin a little bit thicker, and then when we finish the metal, we can thin it out and smooth it and polish it. Um, so these are the guides for the sprueing. So again, sprueing thickness, it's measured in gauge, and the bigger the number of the gauge is, the smaller the thickness of the sprue. Okay. When we talking about sprueing, the sprueing has the purpose of creating a channel for the melted metal to travel through the ring to the invested ring during the casting. So to go from the crucible where we may melt the metal into the ring, into the cavity where we had our wax um, patterns, and to fill that cavity. Okay. So the sprue is a channel through which molten metal will be cast into the mold. The purposes of a sprue channel are to allow an escape for wax during the early stages of the burnout procedure, and to direct the molten metal into the crucible directly into the mold cavity. The channel also provides a reservoir of the metal on which the casting might draw during solidification. We're going to see in the later slides how this process is done. Sprues are made of plastic, wax, or metal, and they are attached to the wax pattern to the base of the sprue. When the sprue is burned out, it becomes a channel through which the metal is going through to complete the casting. To lessen the possibility of distorting the pattern, always attach the sprue while the pattern is seated on the die. So this is very important because sometimes, like I said, depending on the die, sometimes we may have an area on the coping where the wax is a little bit thinner. And if we don't have it on the die, when we apply the sprue and attach it with wax to the wax pattern, that can distort the area where we're trying to attach on the coping. So always do the sprueing on the die. Attach the sprue to the thickest part of the pattern at an angle that will create a least amount of casting turbulence. Usually for a PFM, it's recommended that the sprue should be attached at 45 degrees to the axial surface of the full contour pattern. Place the sprue straight up, not slanted at 90-degree angle for thin copings. So again, for the thin copings, we have to be careful how we touch the sprue, because if we attach it at a 45-degree angle, that may damage the wax, and we might have a miscast. Avoid attached sprue former to anatomical features that are critical to the occlusion that we develop during the waxing. So if we cast a full um, wax pattern, a full contour wax pattern, don't attach the sprue, let's say, to the fossa or to, the inclined plane or the cusp, because that, can damage your waxing, and then it's very hard to reestablish or recontour the anatomy after casting in metal. So there are different type of methods for sprueing. So we have the direct sprueing, where it can be also called as independent sprueing, where we have one sprue attached to the wax pattern. Again, there are many indications for this type of direct sprueing. For fillings like inlay, onlay, partial crowns, complete crowns, we can use single individual sprues. Another important aspect of individual sprues is the reservoir, which is that little ball on the red sprue, and um, that plays a very important role during the casting. So when we cast and we melt the metal, some of the metal stays molten into that little ball in there, and then when the metal starts to cool inside the ring, it's going to shrink, but it can take some of that molten metal that it's left in that little reservoir to complete the casting. So our crown is not missing parts. So direct sprueing, we can use a 10 gauge plastic wax sprue for single coping. Also, we can use 8 to 6 gauge sprue for bridges. The sprue should be straight up, not slanted at 90-degree angle for thin copings, or a 45-degree angle for a regular full wax contour, and also at the thickest part of the wax pattern. When we're talking about also direct and indirect method of sprueing, we can use for direct, we can use the individual sprues with a reservoir. For indirect, we can use what's called a runner bar, and this is the figure that we see here in blue, where the middle part where it says reservoir bar, that's called the runner bar. So that reservoir bar, it's exactly like it was on the previous image on the red sprue, that little ball. So it has the same purpose to maintain that molten metal to complete the casting. And on top of the reservoir bar, we can attach the patterns. The indirect sprueing, it's mostly done for bridges. Also, it can be used for multiple patterns. If we have single patterns, we can put more on the runner bar, but in general, it's used for bridges. In terms of how we attach the sprue pattern into the ring, right? So we have the silicone rings that they have the base and then the top. So in the base, we have a little opening where we have to put the button, the wax button and then we can introduce the wax pattern, sprue wax pattern in there. Now, the most important thing when we attach the wax patterns to the um, the ring, always the wax inside the ring, the wax pattern should be outside the heating zone because it's gonna melt really fast, okay? So we want that area to be outside the heating zone, the thermal zone. So we can see here in this representation what are some of the problems that we may encounter if we don't do good waxing or attach the sprue correctly. So if the waxing is too thin, that can create voids in the casting. Again, if the sprue is not attached correctly to the wax pattern, that can create voids, but also can lead to miscasting, porosity on the cast, many other problems that can be avoided. Okay. Some other causes of porosities are dirty wax, overheated or underheated alloy. So during the melting of the alloy isn't melted at the right temperature. Underheated mold, so the burnout stage wasn't complete, and the sprue were attached to the wrong position to the wax. In terms of how we attach the sprue wax pattern to the investment ring, we have to be careful to have enough clearance from the top of the ring and also from the sides of the ring. And we don't want the wax pattern to be in the middle, where is the heat zone or the thermal zone. So this is some of the illustrations for sprueing and attaching the sprue patterns to the ring correctly, okay, depending on what type of restorations we have to do. Very important also, if we look at this picture, how the wax pattern, if we have multiple wax patterns to be casted, how we gonna sprue them, and what's the distance between them. So we always have to make sure that there is a little space between each wax that we insert inside the ring, because we want the investment to go around each wax pattern and also around each sprue. So there must be a little bit of space in there, so the investment it's strong enough in that area. All right. So if we look at the middle image and we look at the picture B and C, we can see that if we have sprues that are too long, what's going to happen is that it's going to create too much of a space, and then they're going to be probably above the heat zone. If they are too short, then again, we might have a problem with the investment being in that area, but also the patterns must be in the heat zone. So we have to be careful. So again, this is an illustration of the runner bar. So the runner bar, like I said, it can be used for sprueing a bridge, or it can be used for sprueing individual wax patterns. Auxiliary sprueing. So this is very important. Sometimes it can be, it's called auxiliary sprueing or a vent. So those sprues, they're really thin and they're used in an area where the wax is thin, and we might have a distortion during the casting there. So what those vents are doing, it creates uh, a smooth concavity where the wax is thin. So when we melt the wax, when we melt the alloy and it flows into the cavity, it's going to be nice and smooth and complete the casting, okay? So many times, especially for long bridges, long span bridges, those vents are used to ensure that the casting is complete and accurate. Uh, Again, very important for the porcelain fused metal. We have to be careful where we position the wax pattern. So we have to be careful to position the wax pattern outside the heat zone, okay? Because that's going to create too much heat. When the metal goes in, it's going to be a miscast, okay? So again, we saw it for the indirect sprueing. So for direct sprueing, that reservoir, the little ball, has to be in the center of the ring. For the indirect sprueing, the runner bar has to be directly into the heat zone, okay? Um, Today we're using silicone rings, so they're very safe and they're health safe. But in the past, we used to have metallic rings, and we used to use what's called a liner to put it inside the metal ring, and then when the investment will set, that liner, because it was made like from a kind of like a paper, and it will allow the expansion of the investment during the setting time. So that's why the liner was used. Now, many times this liner was made of asbestos, which was very damaging for the uh, dental technicians working with it. Then, they found different type of substitute for that um, asbestos, which were more, um, safe to use. But and still, it was another step introduced into the casting procedure, which a sensitive procedure by itself, and to control the expansion of the investment. So the introduction of ringless rings or silicone rings that we use today is beneficial not only from the healthy uh, reasons, but also because it's more accurate. Investing. So when we do investment, always mix the investment. Um, First of all, find out how much investment do you need for the size of the ring that you use. So sometimes you may use 100-gram rings or 200-gram rings, or whatever the size of the ring is. So read the manufacturer instructions for the size of the ring, how much powder do you need and how much um, liquid. Now, very important also, we have to find out the ratio based on the type of metal we're going to use. So if we're going to use non-precious metal, or you're going to use semi-precious metal, what's the ratio of special liquid and water? And that's important because that's going to give us the retention of the crown, okay? So if the rule is less water, more retention. So if we use more water, it's gonna be a little loose, okay? Well, after we mix the investment by hand, we're gonna put it into vacuum mixer, and again, read the manufacturer instructions for how long we should keep it vacuum mix and what's the pressure in there, and then slowly add the investment into your ring using a vibrator. I recommend not to put the vibrator on high because that may move the wax pattern inside, so very low, and continue to pour up the investment until you fill up the ring. So sometimes for different type of um, restoration, it's indicated to use like a small brush or a very small instrument to flow the investment around the wax patterns so they can take the shape of the wax that we did. Okay. So when we're talking about casting investment, what are some of the properties and composition? So properties, they have to be easy to work with. They have to set in a short amount of time and to produce a smooth surface and fine detail, to not break at a higher temperature during the burnout stage, to not give too much gases that will contaminate the alloy, also to be porous enough to allow the gases to escape during the burnout stage, and when we finish casting, easy to divest and break away from the casting. Also to be sufficient strength to all the temperature. So if we put it in the burnout oven, a cold oven, and then we raise the temperature to, let's say, 900 degrees Celsius, this investment has to withstand the changes in the temperatures. Okay. Um, also, another good property has to be cheap because we're using those type of materials very often in the lab. So if it's expensive, it's very hard to keep up with. Some of the investments are high heat phosphate bound investments that are used with ceramic alloys. Um, those investments only they can be used for non-precious or base alloys, which can withstand higher temperature. The burnout temperature for ceramic investment is 1650 degrees Fahrenheit. Why not gypsum bond? Because these are used for semi-precious and precious alloys. They will break down at a higher temperature and release gases like sulfur and will contaminate the ceramic alloy and cause bubbles in the casting. Um, Composition of the investment material could be refractory metals, quartz and crystalline 60%, binder material, gypsum, silica, or phosphate 35%, chemical modifiers 5%, calcium sulfate investment or gypsum bound are not above 1250 degrees Fahrenheit. Okay, so very important, will break down into sulfur dioxide above that temperature, which is toxic gas. So before we start the investment, also we have to make sure that we use the bubbleizer to break the surface tension of the wax patterns. And like I said, we can use an instrument or a brush to paint the investment on the wax patterns inside and outside to avoid any voids or bubbles, and make sure that It says here the normal setting time bench setting is for 60 minutes, but that depends from each manufacturer. Um, so temperatures and expansion. Um, when we use the bubblizer, before we invest, we have to make sure that the wax patterns are completely dry. If there is any moisture in there, that we would be added when we introduce the investment, and that will change the composition and the properties of the investment. Okay. Um, so we talk about, how we mix it, the ratio between special liquid and the water. And again, we have to be aware of the setting time. So read the manufacturer instructions when they tell you after we uh, invested the ring. Sometimes we may need to put it in a pressure unit for a few minutes to eliminate any air bubbles from the investment and make the investment stronger, and for how long we have to let the investment set before we can put it in the burnout oven. Also, we have to make sure that we know the correct temperatures, okay? So heating expands the refractory metal. So crucible expands about 1.6% more, and the quartz expand a quarter times more. Um, we have to once the burnout temperature is reached, okay, and ring its heat soak at the proper time, okay, we have to cast right away. We can let the ring cool down or reheat it. So let's say the final temperature for burnout stage, it's 1650 degrees Fahrenheit. Once we look at the oven, burnout oven at 1650 degrees Fahrenheit, that's it, we're ready to cast. So we can start proceeding with the casting. Expansion, the investment mixed with water to the specification of the manufacturer controls the retention. Okay, so more expansion if it's mixed with the manufacturer liquid. High temperature, so one time plus the liquid, and high temperature 2 times plus water. More liquid in the mix, it's less expansion, therefore a tighter restoration. Less liquid, more expansion, a looser restoration. Setting expansion, this is very important, take place during the setting time on the bench. After we invest in the ring, we put it on the bench we let it set on the bench, and this is the setting expansion. So this time, if you put your hand on the ring, sometimes it gets hot, and that's the time when the investment starts to set and eliminates heat. Okay. Hygroscopic expansion take place where sometimes the rings are placed in water. To some of the materials for investments, they might require to be set in water. So that's hygroscopic expansion. So again, the same procedure takes place during the setting time of the investment. There is an expansion. So it could be at a setting on the bench or in the water, or thermal expansion that takes place during the burnout of the ring. So when we put the ring in the oven, there is another thermal expansion that takes place of the invested ring. Okay. So the binders, those are some of the materials that are added to the investment material depending on what type of restoration we need to cast. There's a question here. After the investment sets completely, scrape off the top of the ring. Why? So usually we want to either trim or scrape the top of the ring to break the seal of the investment. And when we put it in the burnout oven, that surface, because it's going to be more porous, is going to allow the gases from the melting of the wax to escape. Okay, so this is where the top of the ring is scraped and placed in the oven, burnout oven. So again, burnout procedure, it's a very sensitive procedure. Always follow the manufacturer instruction. Read for the investment and also read for the metal. What type of metal you're using for casting, okay? Some of the investments are allowing us to put the ring into preheated oven directly and let it heat soak for half an hour or whatever the time might be, and then go ahead and proceed with casting. Some of the investments are required to be placed in the burnout oven, in a cold burnout oven, and raise the temperature a certain degrees per minute for a period of time, and then raise the temperature again to the second stage, and then complete heat soak and complete the burnout stage. So again, every time we're using an investment, always make sure you follow the manufacturer instructions in terms of the final temperature of the burnout, how the ring should be placed in the burnout oven, and also the, the degree of temperature rise per minute. If we insert more than one ring in the burnout oven, then we should add additionally 10 minutes for heat soaking. Crucibles. So crucibles, those are the containers where we're going to melt the metal during the casting procedure. Zircon crucibles are more durable than quartz type. They're heat resistant and they're color coordinated because usually when we cast, we don't cast in only one type of dental alloy. We have different. We may have ceramic dental alloy that are 50% gold. We may have ceramic dental alloy that are base alloys. So each alloy should have its own crucible. Okay. Usually on the crucible, you can use like a wax pencil to mark the type of metal it's used for. So every time you're ready to cast, you know which crucible you should choose. Or color coordinated. So you coordinate, let's say, blue crucible for base alloy. Before using them, crucible must be conditioned by using borax powder to seal the surface of the crucible because the crucible usually has like a porous surface, and if we don't condition it, when we melting the metal gets embedded inside the crucible, the surface. They come in different designs to fit each type of the casting machine. Some are horizontal, some are vertical. Do not use the same crucible for different alloys because it will change the alloy composition and therefore their properties. That's very important. So when we do the casting, also we have to be familiar with what kind of casting procedure we use. We can use a torch casting or we can use an induction casting. So a torch casting, we can use what's called a broken arm casting machine. The broken arm, it's referring to the part of the casting machine that holds the crucible where we melt the metal. And depending on the size of the ring, we can turn the the broken arm as necessary. So for instance, if we have 100 grams ring, usually it's about 4 times we can turn the spinning arm, the broken arm, and lock it in place. What that does, when we're ready to cast that, after we melt the metal, we release that broken arm, and because we turn it 4 times, it's going to start spinning 4 times. Okay? So we can we place when we're ready to cast, we're going to place the ingots of the metal inside the crucible. Then we're going to use a torch that's using gas and oxygen to melt the metal. And once the metal is melted, we can release the mechanism that locks the broken arm, bring closer the ring to the broken arm, to the crucible, and then it's going to start spinning. And during the spinning time, the metal, molten metal from the crucible, is going to shoot into the ring and complete the casting. Make sure that the crucible is heated up before we start melting the metal, and also how we know when the metal is ready to be casted. So depending on the type of metal that we use, for instance, if we're using a base alloy, the metal it's going to be kind of like a little bit melted, but it's still the individual ingots is still going to be separated. When we use noble or high noble alloy, all the ingots, when the temperature is right, all the ingots is going to melt together and form like a ball of molten metal. How do we know how much metal we need to use for the casting? And that's very important. So there is a formula for that. So before we invest, we use a jewelry scale. You take your wax pattern with the sprue and you weigh them on the jewelry scale, and you write down the amount of wax, right? And then we multiply that number with the density of the alloy. And the density of the alloy, it's given to us by the manufacturer. When we buy the alloy, it comes in a package, and the package, it tells us the composition of the alloy, the percentage of each element in that alloy, and different properties, including the density of the alloy. So you look at the package, you look for the density, and then you multiply what you weighted your wax pattern with the density, and you find out how much metal you need to cast. When we're doing casting using a torch, it's very important how we adjust the torch, right? Because we're using a gas and an oxygen. So we have to adjust the torch to have enough oxygen and enough gas in the flame to melt the metal. For base alloy, we need more oxygen to melt the metal because it melts at a higher temperature, okay? But very important, what we need to be aware before we start the casting, we adjust the flame to see that inner cone. So we're going to see this blue flame inside the flame. And we're going to use, to melt the metal, we're going to use the tip of that inner cone to melt it, okay? Because that's where the flame is the most higher temperature, okay? Temperature conversion, so this is always good to know the formula, how you convert from Fahrenheit to just Celsius, because sometimes in the US we're using mostly Fahrenheit, but other countries they might use Celsius. And when we buy, let's say, investment or other products from different country or old ones, they might come already set up on the Celsius. So we have to know how to convert temperatures. So this is how the melting looks of the metal. So we start heating the metal, the ingots, until we see that they kind of coming together. This is probably a base alloy. You see they change the color, they become very bright, but they keep the shape. It's still there. So this is how the solidification takes place. So when we're talking about now, we finish the casting, we retrieve the ring from the casting machine, and then we're gonna let it cool on the bench. And during this time, the metal is gonna shrink because it's gonna cool off. So during that cool off phase, that's where that molten metal that it's in the reservoir of the sprue, it gets pushed into the patterns where we have it to complete the casting. Usually when we let it cool, the areas of the wax pattern or our metal, the areas that is thinner, that's the area where it cools are faster and it shrinks more. Then the area that are thicker in metal, that takes a little longer to cool off. Okay, so failures of the casting. So if the runner bar is too small and a button is present, the bar might be casted satisfactorily, but there is a greater likelihood that the restoration will be incomplete. Incomplete meaning if you look at the restorations, the margins are missing. The absence of porosity on the underside of the bar might be an indication that the button supported the bar rather than the patterns. So the problem was the attachment of the patterns to the runner bar. Again, rough casting. A rough casting with multiple nodules might be caused by investing techniques, usually the investment or adverse alloy investment interaction. So when we have these rough surfaces, it's either the investment did react negatively with the casting during the casting procedure, or it was a reaction of the investment with the setting. Fins. Fins can be caused by the excess wax pattern cleaner or improper heating of the mold, so during the burnout procedure. Divesting, so very important when we start to retrieve the castings, okay? So never divest the ring when it's still hot. Let the ring bench cool completely, and then we can use a hammer or a mallet to break the investment, but always hit it in the bottom where the hole is. Don't hit it on the sides because you might damage the margins of the restorations, okay? Sandblast the metal with a 50 micron aluminum oxide, and make sure that you move the nozzle of the sandblasting unit so you don't poke a hole through your metal coating. Aluminum oxide is used to perform this procedure of sandblasting, which also removes the investment on the surface of the casting, but also condition the metal to receive porcelain. Finishing the metal. So it's very important that before we apply the porcelain, to read and understand how we should finish the metal from the manufacturer recommendations. Okay, different metals might require different type of conditioning. Some of them might require pickling. Some of them might requiring more sandblasting, degassing, and other procedures. So grind the metal surfaces for porcelain application with non-contaminated aluminum oxide stone in one direction. Blast do not recycle or new 50 micron aluminum oxide do not exceed the blast pressure of 4 bars at 60 psi. Clean in distilled water and ultrasonic unit for 10 minutes. Finish the metal with non-contaminated aluminum oxide stones, white or pink stones. Do not use the heated stone or ceramic alloy because it produces changes in the grain of the metal, make it more porous. Grind the metal in one direction parallel to the margins only. Do not trap air because that's gonna cross-contaminate your porcelain. Reduce the metal to 0.25 millimeter only if needed. Sandblast again with the 50 micron aluminum oxide at 60 psi. And after that, do not touch the casting with your bare hands after blasting because the oils from your hand will contaminate the surface of the metal. That will also make the porcelain maybe not to stick to the surface. Clean in distilled water and ultrasonic for 10 minutes or use a steamer. Okay. Degassing, this is another procedure that is done to condition the metal before applying the porcelain. So degassing is the highest temperature that we can put the metal through. Again, make sure you read the manufacturer instructions to see the degassing temperature. And again, you can use a program in your porcelain oven that reaches the desired temperature. The holding time, the vacuum is very important. The vacuum pressure. Okay, so this all contributes to removing the oxides from the metal, so it's conditioning the metal to receive the porcelain. It's important also before we start applying the porcelain, the first layer of porcelain that should be applied should be a wash of opaque fired at a higher temperature because that creates a stronger bond between the porcelain and the metal framework. When we polish, we have to be careful that we're using a polishing compound for metal, so we can use Tripoli or Rouge or other similar products. If we polish the metal after the porcelain is applied, we have to make sure that we're using a type of polishing compound that it's not contaminating the porcelain surfaces. Okay. Also, we can use stones, silicone wheels, rubber wheels, and points, and bristle brush with polishing compounds to achieve a high shine. To finish the restoration, we have to steam and use ultrasonic to clean up the final cleanup of the restoration, disinfect the finished restoration before sending it back to the doctor. Another procedure that it was done routinely in the lab was a soldering. So let's say we have a bridge that we do the framework for a bridge, and the doctor said, you cast the framework, you send it to me, I'll try it in the patient's mouth, and then if everything is good, I'll take an impression, a pickup impression with that framework, send it back to you. We're gonna do another model, and we're gonna apply porcelain and finish the restoration for the patient. Okay. But when we send the framework to the dentist discovered that the framework doesn't sit properly. It rocks right in the patient's mouth. So what he can do, he's gonna cut it. So one, let's say, one contact or area is gonna be broken. So the doctor takes the disc and he cuts the framework where he feels like it's not seated properly, and then um, he or she can take some uh, acrylic, put it back in the patient's mouth, and use the acrylic to hold the the bridge together in the position that it's needed. It's correct. And then they send that back to us, and now we have to perform what's called the soldering. So we have to put those two pieces of the bridge together in the correct position. So how we do this, we're using a different type of investment that it's called a soldering investment. And we're going to invest the bridge, and then we're going to use a metal, a melted metal, just to um, apply metal in that little space between the two parts, the two pieces of the bridge that we need to solder together. So the soldering investment, it's has different properties. It's not the same as the investment used for casting. There are two different type of investments. So this one is a low setting and low thermal expansion. um, Expansion must match the shrinkage of the solder, and the solder it's the same. It's actually not the same. It's a comparable alloy with the parent alloy of the framework. Okay, and the soldering investment they fail if they're not properly used. If there is too much water, and this is another thing, soldering investment doesn't use um, special liquid, so they're mixed by hand and with water. So if there is too much water in the soldering investment, when we put it in the oven, it can break. So again, read the manufacturer instructions and make sure that you use the same amount, the recommended amount of powder investment to water ratio. This is not a procedure that it's done daily or routinely in the lab anymore, but it's a sensitive procedure and requires a little experience. And I think this is it. So if you have any questions, please ask. Thank you.